Alright guys, so now we're going to talk about an addition mechanism that some of you guys might already be familiar with. But regardless, we're going to talk about it in this section because it has to do with addition. And that's called catalytic hydrogenation and also Wilkinson's catalyst. So let's go ahead and check it out. So basically, catalytic hydrogenation is a way of adding hydrogen to double bonds. So remember that I said that any addition reaction is a reaction that you take one pi bond and you make two sigmas. Well, actually, one of the easiest ways that you could do that is just to say, let's take that one pi bond and make two hydrogen bonds out of it, okay? That would still be an addition reaction because I'm taking one pi and I'm making two sigma bonds, all right? And that's what happens with both of these reagents, okay? So how does this work in general? Basically, we're going to have a double bond or a triple bond, and whenever you have one of those, we're just going to add as many H's to it as possible. So what that means is that the product of these reactions is simply going to be alkanes. Okay? So we haven't learned a whole lot of reactions that make alkanes. This is one of them, because you can take double bonds and triple bonds, add hydrogens to them until they're fully saturated and become alkanes. All right? So the stereochemistry for this reaction, both of these is going to be syn addition. And what that means is that your end products would be cis products. Okay? What that means is that your hydrogens are going to add from the same side of the double bond at all times. And why is that? Because it turns out that our intermediate, or the thing that's going to catalyze this, is going to be a metal catalyst. Okay? And that metal catalyst is going to come in and it's going to coordinate the H's to be on one side of that double bond. So that's why you're always going to get syn addition. All right? So now, for these two things, I'm actually going to kind of ignore them. There's no carbocations, so I'm not going to expect rearrangements. And then I'm adding two of the same thing. I'm always adding two H's. So I don't really have a choice between mark and anti-mark. In fact, that's not really going to apply since I'm adding two of the same thing. All right? So let's go ahead and see the general reaction. The general reaction basically looks like this. I have two different mechanisms and two different reagents that do the same thing. This combination of reagents here is called catalytic hydrogenation. Okay? How do you know that it's catalytic hydrogenation? Because you've got H2, sorry, a little crash accident there. Because we've got H2 with a metal catalyst such as nickel, platinum, or palladium. Whenever you see H2 with one of those three, that means it's going to be a catalytic hydrogenation. Okay? But there's also another reagent that does a very similar reaction, and that's if I have H2 over what's called rhodium. This is the Wilkinson's catalyst. Okay, I'm just going to write that here. Wilkinson's catalyst. Okay? And the Wilkinson's catalyst is really going to do the same exact thing, just using a different metal catalyst. It's going to have a rhodium and then 3 triphenylphosphenes and a chlorine. You don't need to be able to draw this. What's important is that you just recognize that this is going to do the same thing. It's going to add 2 H's for every double bond that it encounters. But it's not going to do anything else to anything else. So that means that my general reaction, what I would expect is that I get the same carbon backbone as I had in my beginning. I would get a single bond there. Even my alcohol doesn't change. Nothing changes about that. The only difference is that now, instead of having that double bond on this side of the molecule over here, now I'm just going to have 2 H's. So in fact, I would just draw it like that. I don't need to draw the H's because H's are implied. Okay? And then over here, what I would expect is that I would just have a single bond. Why is that? Because basically there were 2 pi bonds here. What that means is that I add 2 hydrogens for every pi bond. So I would have added hydrogen here, and then I would have also added hydrogen here. And that's what I get at the end. What I get is 2 hydrogens here, and, well, I'm sorry, 1 of each color. 1 there, and 1 there. And then I would get a hydrogen there, and a hydrogen there. Those are the 4 hydrogens that were added through my 2 hydrogenation or Wilkinson's catalyst reactions. Maybe you're wondering, hey, but Johnny, doesn't this carbon need to have 3 H's? Yeah, it does. It has that last H that came from the original compound. Remember, there was always 1 H at the end to begin with. That's that H right there. But now what I did was I added 2 blue H's from the first equivalent, and then I added 2 red H's from the second equivalent, basically giving me an alkane as my end product. Does that make sense? Cool. So what I want you guys to do now is I want to just provide the products for the following reaction. That means you're going to have to recognize what it is, and then think about the stereochemistry if it's required, and try to draw the end product. Now notice that instead of using H2, I'm using D2. But that's really the same thing, because remember that deuterium is just heavy hydrogen. So go ahead and try to draw the end product for this, and then I'm going to go ahead and explain it to you guys. So go for it.